How much do you really know about magnetic fields? You might have heard about their healing powers, but what about their hidden dangers? We're cutting through the noise to reveal the real science behind magnetic fields and their profound and sometimes startling effect on human biology. I'm Ben, this is Physics or Bust. Our planet is wrapped in an invisible armor, a magnetic field born from molten iron deep within the Earth's core. It's much more than just a compass guide. This geomagnetic field is our first line of defense against deadly solar and cosmic radiation. Without it, life as we know it would never have survived on this world. While we can't feel this field directly, it's quietly shaping our biology and guiding many more life forms than we ever thought possible. For over a century, we've known that migratory birds and sea turtles use Earth's magnetic field for navigation. But recent research is rewriting the story, showing that salmon, certain bacteria, crustaceans, and even cows and deer use Earth's magnetic field for their navigation. Researchers have been able to study this even better recently, because with the Earth's magnetic field getting closer to a pole shift, it's weakening more and more each year, leading some animals to end up far from where they would usually have migrated. And humans? We have a magnetic sense too, though it might not be as strong as other animals. It's still there. One study found that when people were exposed to rotating magnetic fields, brainwave patterns shifted subtly. And as Earth's magnetic field starts to weaken more and more, I think we're going to find out that our biology is affected by Earth's magnetic field a lot more than we originally thought. Earth's core isn't the only magnet, though. Magnetic healers date back to Greece and even China. The main claim? That the magnets attract iron in the blood, increasing circulation and somehow realigning the energy of the body. But here's the problem from the physics perspective. The iron in the blood isn't ferromagnetic. It's bound in a molecule where magnetic effects are extremely weak, too weak to be influenced by a static field from a bracelet or mattress. Most commercial magnetic devices produce static fields in the range of tens to hundreds of millitesla. Compare that to an MRI, which operates in the 1.5 to 3 Tesla or higher. The MRIs are multiple times stronger. Even in an MRI, the field's effect isn't to pull around the blood. It aligns the magnetic moments of hydrogen nuclei for imaging purposes. So why do people swear they feel better when they wear magnetic bracelets? Part of it is the placebo effect. People feeling better because they did something, even if that something really is nothing. It's amazing what the human brain can do when it thinks you've done something. Now, the placebo effect is a real measurable change in how the body processes pain, but it's not because of the magnetic fields. Now, this isn't to say that magnetic fields don't have an effect on the body. They certainly do. When it comes to medical magnetism treatments, one of the big differences that I see is the difference between static magnetic fields and changing magnetic fields. Take transcranial magnetic stimulation, for instance. A coil generates a rapidly changing magnetic field, which we know by Faraday's law of induction generates electric currents. And because it's a directed changing magnetic field, the currents are induced in targeted regions of the brain where there's neural activity, sometimes dampening overactive networks linked to depression or boosting underactive ones, depending on what's prescribed by the doctor. In physics terms, the difference is clear. Changing magnetic fields produce electric currents, which can definitely have an effect inside the body, where they can influence charged particles in neurons and other parts of the body. Whereas a static field from a bracelet does not do much at all. Some of the other research on magnetic health effects focuses on precision, both in field strength and frequency. Pulsed electromagnetic fields, or PEMFs, use time-varying magnetic fields in the low frequency range, often between 1 Hz and 100 Hz, and a field strength in the micro to milliteslas. At these frequencies, the induced electric fields can interact with ion channels, tiny protein gates in cell membranes that control the flow of calcium, potassium, and sodium. In bone cells, for instance, PEMF exposure can trigger signaling processes to increase osteoblast activity, cells that lay down new bone matrix. That's why PEMF devices have been used in certain cases for delayed bone healing. On the neural side, weak magnetic fields can nudge the membrane potential of neurons closer to their firing threshold. Not enough to cause uncontrolled firing, but enough to alter how brain networks synchronize. That's why researchers are testing low-intensity magnetic stimulation for traumatic brain injury, Parkinson's, and Alzheimer's. Physics explains this selectivity. The induced electric field depends on the rate of change of the magnetic field and the geometry of the target tissue. A fast-changing localized field can focus effects on millimeter-scale brain regions while leaving surrounding tissue untouched. The same physics that makes magnetic fields useful in medicine also means that they can cause harm in the body. If a static magnetic field is strong enough, like the 8 Tesla experimental MRI scanners, they can create intense Lorentz forces on any conductive loops inside the body. Normally your tissues are poor conductors, so the effect is minimal, especially since the strength of the static field isn't usually that strong. But even subtle induced currents can stimulate nerves and muscles, especially if the field changes rapidly. This is where Faraday's law and Ampere's law come back into play. Faraday's law says that a magnetic field induces an electric field, and Ampere's law says that an electric current produces its own magnetic field. So if we figure out how to affect brain tissue with low-intensity magnetic stimulation, what's to keep someone from affecting a good brain to do bad things? The fact is, long-term exposure to high magnetic fields, particularly those at extremely low frequencies, has been connected with not only neurological issues, but also cancer. When your retina experiences induced currents, it responds with magnetophosphines, those flickering lights people see in changing magnetic fields when it's around 20 to 50 millitesla at certain frequencies. But not all electromagnetic exposure comes from devices whose purpose is to create magnetic fields. Every day, millions, if not billions of people keep wireless devices, smartwatches, phones, earbuds, right next to their body for hours on end. These devices emit radio frequency electromagnetic waves, not static fields and not low-frequency magnetic fields. Most of these devices have been made to operate with 5G technology, which means they're operating with frequencies sub 6G up to about 24 to even 100 gigahertz. At these frequencies, the photons don't have enough energy to ionize atoms, like X-rays or gamma rays would, but they do interact with cells and molecules. Many scientists posit the primary safety risk as the specific absorption rate, a measure of how much RF energy your body absorbs in watts per kilogram. Regulatory limits are set to keep the threshold well below safety concerns. The big question is whether non-thermal biological effects exist, changes that happen in cells or tissues that aren't due to heating. Laboratory studies have reported subtle effects on cell signaling, oxidative stress, and gene expression under certain RF exposure conditions. On the other hand, there's been a large number of studies on humans that haven't found consistent evidence of health hazards at exposure levels within safety limits. Still, the research is ongoing, and given the rapid adoption of 5G and the fact that these devices stay in contact with us for hours at a time every day, scientists need to be on the watch for long-term trends. Magnetic fields aren't magic, but they're also not just background noise. From subtle shifts in cell behavior to protection from solar and cosmic radiation to induced currents in the brain, magnetic fields are a powerful feature of our universe. And the more we learn, the more we realize understanding the physics behind magnetic fields is the only way to harness their potential. So what other important effects do magnetic fields have on the human body? Let me know in the comments below. For more updates on science and technology, remember to like and subscribe, and remember, keep asking questions. I'll see you on the next video.